Hello, everyone. Thank you for joining us today. So we got a few requests for recording this talk. So if the talk will be recorded, so if you can start that, please. And today my name is Alberto Comazzi. I'm the PI of the NASA Astrophysics Data System. And it is a pleasure to be welcoming Jo Ciuca from ANU, the Australian National University, where she's a fellow, and she has interest in both astronomy and machine learning and AI, and this is what the talk is about. It was great to meet Jo, through actually Twitter and our common friend Josh Peak, who gave a talk yesterday, and now there's a group of people who's very excited about things that she's been doing, including Alyssa and other people that you will hear about shortly. So I will let Jo explain exactly what it is that she has been experimenting with and how this may be useful, not just to astronomy, but to the rest of science someday. Jo?
Thank you so much, Alberto. Can you hear me all right? All good? Hi, everyone. My name is Ioana Ciuca, but my non-Romanian speaking friends and colleagues, I go by Jo. I'm a Jubilee Joint Fellow at the Australian National University, working as part of two schools, the Research School of Astronomy and Astrophysics and the School of Computing. And today I'll be talking to you on behalf of UniverseTBD, and together with my colleagues Jan Santing and Kartik Iyer, who are here, we will be telling you a bit about how we can create new horizons in astronomy research using foundation models. So a brief outline of the talk is the following. I will start by introducing who we are and why we do the work that we do. Then we'll quickly go through a small primer on large language models and why they are important to astronomy research. Then I will briefly discuss the attention mechanism that sits at the forefront of the latest advancements in natural language processing. And then Kartik will briefly introduce embeddings, which are the way we understand language and we transform it to numbers so then we can actually model it and experiment with it. And in the very last 2 points, I'll discuss with you the work that we've been doing as part of UniverseTBD to interact with astronomy literature in two ways. First, we will see how we can use large language models to retrieve information from our papers. And in the last part, I will show you how we can use large language models to come up with new ideas that can help us do our research. So to the people here who have asked me why UniverseTBD, I hope that this slide answers your question. Kartik and I were in New York in Flatiron discussing how we should name this collaboration. And we started by saying, okay, we definitely have to have the universe there somehow. And then we were like, okay, maybe we should also have something about it, but SpaceX was already taken. UniverseX sounds a bit very, very scary. And we said, to be decided, and it stick. So, but who are we actually? So we are a team of 42 plus Earthlings who are actually volunteering their time. So this is on a non-paid basis. And we are astronomers, computer scientists, software engineers working across the whole world. We are 4 continents working on this. And we are grouped in 6 teams working on different components of the project. So here we have team embeddings, team prompting, team fine-tuning, evaluation, make it happen, and take us to the moon. And one of the most important teams is the team collaboration here. And I would like to take this moment to thank Alyssa and Alberto and Kelly and the NASA IDS team, as well to all of you for having me here today and allowing me to tell you about our work. And of course, this slide wouldn't be the same without an ASI, which is a variation of a selfie. Here we have Kartik leading the team embeddings. He's going to talk about his work as part of the UniverseTBD team. Team prompting, this is me and Janssen, who has spent a terrible amount of time in the matrix with GPT-4. Then we have here Josh Nguyen, who's a brilliant young student moving to University of Pennsylvania to do advanced research in NLP. Then here we have Josh, who's leading the evaluation team, and we're very happy to have him here. And Team Make It Happen, these are the young people who are working to make all of our code available to the community, putting things on the cloud and beyond the cloud, hopefully. Maya and Sandor Kruk, he's one of the very few other Romanian astronomers. He's currently working for ESA Archives. So he's the right one to lead this effort, and I think Team Take Us to the Moon is the one where we can do really unique things, like, for example, come up with a new transformer architecture in the future. So what are our goals for UniverseTBD? Our goals are to explore, not exploit, the potential of large language models and multimodal large models for science. We want to identify...
Can we screen share?
Yeah. How? Please screen share.
Zoom.
Right. Yep. These things happen. How do I...
Share screen.
Share screen. This one, right?
Yep.
Yep. Now play. All right. Sorry for that small interaction. It wouldn't be technology if it didn't challenge us sometimes. Can you still see my slides? Is this a bit of a...
Click the thing that says more and do hide. Sitting in the middle.
Where?
Yeah. So,
And that is good that I work part of a team
Wait,
because...
I can't see the mouse actually.
Yeah, I am terrible with these things. Where does it hide? There we go. Hide.
hide
Video.
floating the controls. How many lower?
Oh, I learned something new today. This is brilliant. All right, can you see it? Yeah, you can see it. All right, so as I was saying, we want to explore the potential of large language models and multimodal large models. Multimodal here meaning that we are not only just using text, we're using other sources of data like images or video for science. But more importantly, we want to identify and implement practical downstream tasks such as question answering over our literature. And Josh actually proposed a very brilliant idea with Janssen. We want to also try to keep track of the expanding body of literature. Not only just the literature, but also the code, the interaction with the literature of the data and the code. And finally, we want to explore pie-in-the-sky ideas, such as hypothesis generation. And I will show you very briefly what I mean by that. We also want to build evaluation data sets for science GPTs, because our effort is not singular. Our effort lives as a part of an ecosystem. And other people will come up with their own large language models, hopefully, and we can use these data sets to truly validate their performance. And finally, and I think one of the if not the most important thing, we want to share our findings with the community amongst us. And this is why I'm here at the offices of NASA IDS with my colleagues. We want to see how what we do can actually benefit this extraordinary research effort. But now that I introduced the UniverseTBD collaboration, I want to talk to you a bit about large language models. So large language models are part of the natural language processing research field. NLP sits at the intersection of three other fields: artificial intelligence, computer science, and human language. And when I say large language models or foundation models, what I mean by a foundation model is this is a very large model that has been trained for a long time on a lot of GPUs using many, many gigabytes of data, or even more than that. And these models are very good at a lot of tasks, but they can easily be adapted to other tasks. This effort wouldn't be possible without Dr. Alan Turing. Yesterday, we have 69 years since he's passed away in Manchester. And many people recognize Alan Turing as the key figure in breaking the Enigma code in the Second World War. In 1950, after the Second World War finished, Alan Turing moved his efforts to truly answer this question: can machine think? He published this paper, Computing Machinery and Intelligence, in Actionable Psychology and Philosophy Journal, which shows his forethought at the time. This was still, but back in the day, this was still something that was very, very new. Alan Turing proposed an interesting thought experiment, the imitation game. In this imitation game, you have three components. You have a human evaluator, a machine, and another human interacting. And it is said that if the human evaluator cannot identify which is the machine and the human, then the machine has passed the Turing test. And I'll come back to this question, can machines think, later on in the talk. But you know, one of the first machines or chatbots was ELIZA. And ELIZA was actually created by Josef Weizenbaum here, very close to Harvard, here at MIT, in 1966 at the MIT Media Lab. And here I found a very nice visualization online. Someone actually coded the ELIZA Doctor script. And here, for example, I said, hey, I'm feeling quite nervous today. And then chatbot came to me. Did you come to me? Because you're feeling quite... It actually made me more nervous. And, and then I said, hey, can you help me? And I said, don't you believe that I can help? So this was become a very passive-aggressive response. It really... I was worried. After the interaction with this machine, I was worried. This is 1966. This is 1966. Now, why they call it the present, some of you might recognize this because they say it's a gift. Now we have GPT-4. This is, I think, 100. We don't know exactly the size of it, but this has hundreds of trillions of parameters. And here I went and asked the same question. I'm feeling quite nervous today. GPT-4 is a very nice friend, AI friend. I said, I'm sorry, how can I help you today? So then I said to GPT, I'm trying to see how I can explore large language models for science. And then of course, AI is very hard. Wait for it. And then he says, OK, I understand how you're feeling. This is very hard. But then, this is the funny part. When he says, it even gives me solutions within, this is the second answer that it gives me. When it comes to science, there are multiple ways you could utilize the models. The first one is literature review. And the second one is hypothesis generation. And at the very end of my talk, you'll see that these two tasks we've actually been able to try to tackle. So within two answers, GPT-4 has already set the direction of our field. Now, GPT-4 is not just the only one. GPT-4 is the latest and the state-of-the-art model in an evolution that has been booming since 2017 with the introduction of the transformer architecture by Vaswani et al. Now we have that is pretty much the fire. That is the fire moment that has allowed the great boom of these large language models. And now, moving forward, I think I will introduce my colleague Jansen Ting here, who is truly our co-pilot in statistical machine learning. And he will tell you a bit about what has changed between the ELISA moment and the GPT-4 moment. And hopefully you will appreciate why I think these things are absolutely incredible. It's
the cross.
This.
Okay, but can I take the cross? Okay. Okay. So I am the cameo number one. So we'll talk to you a little bit about what has happened. So I'm a professor both in computer science and astrophysics. It's good to be back. So what has really changed from ELISA to ChatGPT-4? So I think most of us here are not working in machine learning. So I thought I want to give you a very brief overview. And Josh made a very great introduction yesterday. Most of the thing that we care about in astrophysics is not A or B. It's always a continuum between the modeling and the learning scheme, right? So it's always whether or not I want to do the modeling or want to do the learning scheme, but it's a true continuum. So what is very exciting about deep learning is that it's really opened up ways for us to put ourselves in this spectrum. So think about a binary orbit, so it would be on the left-hand side, a pure modeling. Think about linear regression, classical machine learning, is still very strong assumptions. We're assuming that the data fall onto a hyperplane. It's more on the modeling side than the learning side. So Josh yesterday mentioned that you can go just the classical perceptron networks, a fully connected network. So that will be the learning side. But of course, if you want to go full learning, then you require a lot of data. And this is why it's really, really hard. And for a statistician, we have come up with different tools that fall onto this continuum. So think about the Gaussian process is very exciting for statistician because it somehow fall in between the modeling and the learning. You're making a lot of assumption, but you also leave quite a lot of freedom for you to tweak. But you think about convolutional neural network, as Josh mentioned, it's actually more on the modeling side because you're making some assumption about the data structure. So it's never pure learning, it's always between the modeling and the learning side. So you can think about convolution, there are this algorithm, but what fundamentally you are assuming is what we call inductive biases, is that you're assuming there are some data structure that you have to fulfill. For images, meaning that you are either translational invariance or distortion stable, meaning that if I distort a cat, it's still the same cat. If I move a cat, it's still the same cat. This is, of course, a very, very strong assumption. It do not, most of the data set that we care about would not follow the same symmetry. So, for example, if you think about sentences, of course, that would not satisfy the symmetry because most of the sentences are high entropy objects. So your information is sparse, and they also have a long range information. And this will be the same. So all the information, of course, are long range, right? So this is why the booming of deep learning allow us to come up with the other architecture that will satisfy different type of inductive biases. So one of the first breakthrough that leads to this fire is what we call the attention mechanism, which also leads to what we call the transformer model. So you're making a very little assumption, but it's not without assumption. So the transformers say most of the languages actually have long-range information. And this is a seminal paper, 2017, get about a 70K citation. And because of that, the first revelation is that attention is what you need. And then people quickly adopt that. To apply that to languages, this leads to BERT. So BERT is in 2018, so they try to do somewhat a supervised task. So what BERT is a simpler task. Is what we call a discriminative encoder, right? So think about, there are two ways to describe your data. One is a more hard part, called the generative task, meaning that you try to describe the distribution of the data. And the other is a simpler part, what we call discriminative models, which is finding the boundary of the distribution. So what BERT try to do largely is the easy one, and leave the hard part not done. So you can think about this supervised or unsupervised. At that time, most people are pretty pessimistic, because we know that the transformer is amazing, but it's also a very weakly inductive bias model, meaning that you make very little assumption about the data. Also means that you are more data starved. And this is where the venture capitalists change the world, because this is where the OpenAI comes in and ask the most profound question that all humanity has asked, which is, what if I have a shitload of money? And the second revelation is that not only the attention is what you need, but rather is money is all you need. Because what happens is that even you are very weakly, have a very weak inductive biases, as long as you have enough data and big enough models, you can still capture that. So you break open the task from discriminative task to a purely generative task. This is the second big changes. But turns out that the fully generative task is still extremely hard, because this is a very hard task. So the third revolution comes in around 20 or 21, which is what we call the RLHF, reinforcement learning with human feedback. Turns out that because the pure unsupervised task is too hard, you still want to give some guidance to the machine. So it's not you're moving between supervised and unsupervised. The sweet spot turned out to be somewhere in between. And this is leads to what we call the instruct GPT in 2021, also leads to what we call the GPT 3.5 and GPT 4, right? And there are lots of things to be learned from here. One is that machine learning is really a true spectrum, so it shouldn't be really hung on to one thing, but rather to find the sweet spot between the modeling and learning, and also find a sweet spot between supervised and unsupervised. And the other thing that is important to remember is that for a very hard task, like the languages, the model is not important. The data is what is important, right? So you need the money, you need a well-curated data, and both of them, you have it here. So I will let Joseph continue. This is a small copy.
Thank you so much, Ernst-San, and I hope this provides enough context for why we think that our work aligns very well where the advancements are at the moment. But I want to go back a bit to the transformer architecture, because it was so instrumental in getting us here. Transformers, as we see, they are highly used in natural language processing tasks, but they are also used across other domains, such as computer vision, reinforcement learning, translation tasks, and speech. But to all the scientists in the room today, we also use transformer architectures for science. And here are just some of the examples where we can actually employ them. We can employ them in time series data. We can even employ them in galaxy morphology classification, exoplanet studies, and so on. And here I also showed astroconformer work that a colleague of mine from ANU has done, where they even used stellar light curves for transformers. But it wouldn't be the same if I didn't mention the brilliant work that the colleagues here at NASA IDS have done with AstroBird, taking the transformer architecture and using it for astronomy literature. And this work inspired us to also want to work on these tasks. And moving forward, I want to sort of prime you here in a sense that your attention is all I need. So right now, I'm actually going to ask you to what is the sum of all cards. So you have all these cards here on this corner, and immediately your attention goes to the red cards, and you compute the sum. In a similar way, I want to propose you this idea. This idea is generated by GPT-4, as I will show you at the very end. And if you want to read this very long text, what you will fundamentally try to do, where do you pay attention if I ask you the question, is this a good idea? This text will fade away, and after you read this whole text, some things will start popping up. You might actually look at the peripheral regions of the galactic globular clusters. You might say, okay, a good idea looks at the higher, like the more global instance, the hierarchical assembly of the Milky Way. We also want to use good models. So you might say, oh, probabilistic approach. Oh, is that a good reference in this context? So you will start paying attention that you as experts have, you might start paying attention to those tokens, to those word sequences that match your expertise. In a similar vein, I can actually ask you, is this a good critique? As before, the text, you start paying attention to those things that match your knowledge. So for example, with a good critique here, you might actually say, okay, is this critique addressing the selection biases in various surveys? For example, does it include, in this case, the Milky Way, including its non-steady state nature? How broad is the critique? How deep is the critique? So your attention will be immediately primed to those things that match your expertise. So attention, same as for humans, in a machine, attention is pretty much a neural network layer that learns to select relevant parts of the input. Suddenly, the transformer architecture, which to many people looks as a black box, or in this case a pink and green box, can be decoded, can be unveiled. So we have here this encoder part, which pretty much takes an input, moves it into a vector space, and then tries to create a richer context-aware representation of that input. The decoder, where most of the generative task, is done, this takes this representation and generates an output sequence. So the next token in a sequence in an autoregressive manner. And what I mean by autoregressive, say, oh, if I have predicted this next word, then when I predict the one after that, I'll also take this previous word into account. And at the very core of the transformer architecture lies the exact same attention mechanism that we have played with earlier. But nothing would be possible if we couldn't transform words into numbers. So how do we actually make that transformation in a meaningful way? That is where embeddings come into place. And now I'll give the floor to my colleague Artiger, who is leading this effort, and he can tell you a lot more than me how to do this, achieve this task in a meaningful way.
All right, cameo number 2. So I'm Karthik Iyer. I'm a Hubble Fellow at Columbia, and I have a really hard time keeping up with all the literature. All of you are way too productive. So I came at this from an approach where, in addition to things like ADS, I wanted to build tools that help, search for relevant papers so that you don't forget to cite them. And I built something way back in 2019. It worked somewhat well, and then I abandoned it because traditional ADS was still state of the art. And then I met Jo, and she's like, hey, why don't you try this with GPT-3? And this is sort of where I went with it, and it turned out to be really fun. So I can also do a demo of this at the end of the talk. But, okay, there is considerable risk in asking things like BARD or GPT-3, any of these large language models, to answer questions based on the entire corpus of data that it has been trained. And that's because all of these transformer models they're generative, as Johansson said. And so that means that they can generate text without necessarily having to be truthful, right? So this phenomenon is called hallucination, and it often happens that sometimes it can be egregiously wrong and lead to real-life consequences like the stormtrooping. And so that's bad for them, and it's bad for science if we use it for science. So that's something we want to avoid. And so instead of considering the whole of the transformer as one unit, right, we can look at what's happening between the encoder and the decoder. And because a computer by itself is not understanding words, right, it's trying to work with some kind of abstract vector space. And so that's what embeddings are. Embeddings are the intermediate layer that sort of take all the inputs that we think of, whether it's images, text, plots from papers, speech transcripts, what have you, and converts it to vectors in an n-dimensional space. Right? And these are things that are more easy for computers to play with and somehow more easy for me to play with because it sort of allows me to start visualizing the landscape of the training data and seeing what's going on under the hood. So this is sort of like the n-dimensional space, and I'm bad at visualizing things in n dimensions, so I tend to project it down to something like 2 or 3 dimensions. And because in my day job I am a galaxies person, so I took a corpus of galaxy evolution papers, the 30,000 most recent papers, and sort of did this embedding trick with it where I ran it through GPT-3 and sort of projected it into this 2D space. So each dot here is a single paper, right? And the nice thing about this is that once you have something like this, where you have a 1500 dimensional vector corresponding to each paper, you can start doing all sorts of interesting things with it. And this is sort of a similar embedding that Google released for code on Stack Exchange. So it's sort of the naive application. The simplest thing you can do is once you have an embedding, you can figure out what different areas correspond to, right? So you can be asking things like, so are there clusters? Are there significant structures? Are there missing areas, right? All sorts of things. The things to keep in mind is you can't just use an embedding to solve all of our problems because it's only as good as the input data, it's only as good as the awareness of the context. So the reason I did this in 2019 and stopped using it is because things like GPT-3 weren't out yet, and so my models were not learning context, they were only learning keywords. And so that means that when you ask it to do this grouping, it doesn't really get the fine structure right. So if you can now have models that produce context-aware embeddings, where that vector that it produces has some information not only about the set of words in a corpus, like just an abstract output text, what have you, but actually has information about the arrangement of that words, that carries a lot of information that's valuable to us. And finally, when you ask an embedding questions, you want to make sure that the space that that vector maps onto, the vector of any question you ask, has to lie in a reasonable part of the space where you want to look for answers. So there's all of these fancy ways of searching for similar vectors that have come up in the last few years. Alright, so 3 quick applications and then I'll throw it back to Joe. Number 1 is similar to what I showed. So if you have this galaxy space, you can ask it all sorts of questions and see where papers sort of on that subject lie. So you can ask it things like, essentially papers that are written using a certain telescope, right? Live on very different paths because they do different science. People who look at the CGM, ISM and IGM tend to have overlapping interests but still are distinct in key ways. Quenching and Asian feedback are related but not the same, right? And machine learning, neural networks and deep learning all appear in abstracts in mostly the same area with some interesting like branching out that shows you how people tend to use Java to talk about their methods. So this is great, there's lots of interesting exploration to do here. But then you can also look for similar vectors given a question. So this is sort of the main use that I envisioned when I made this, where you can have a small tool where you can ask it questions in natural language, right? You don't have to try to phrase it to optimize keywords or anything. You can just write out a question as you're thinking it and tell it to essentially give you small paper summaries, and it sort of digs up relevant papers and gives you summaries. And the reason I'm happy with this is because I wrote a paper and then I built this tool and I searched for relevant references and it gave me a bunch of things. And then 2 people emailed me saying, hey, you didn't cite my paper, can you cite my paper? And it was on this list. And I was like, wow, okay, good. Might actually be useful to cite. And the third thing that we are all excited about is to see if it can actually answer questions. So this is again with data that was collected in mid-June-ish, and I asked it what's the highest redshift galaxy found with JWST, and it's like, oh, redshift 15, and it gave me a source, right? So here's the thing where we can make sure it's not hallucinating, because when you're doing the sort of embedding-based search, you can collect nearby papers and use it to make it give you an answer that also cites the sources that it used. So it gives me the paper where it did that, and I'm like, okay, yeah, but that's photometric. So I'm like, what's the highest spectroscopically confirmed galaxy? And then it gives you a paper that does that. But both of these are single paper results. So then I asked it, how does quenching timescales change as a function of redshift? And here it gave me a more vague answer, but you can see that it drew from multiple sources to formulate the answer. And so if I want to go read more and make an informed opinion, it can do that. So I can do it and move with this at the end, but like the thing is that this forms the basis for the stock price maybe to not go down, and think of all sorts of applications.
Thank you so much, Karthik. So I hope now that you are a bit more convinced of why we think these large language models are useful for the astronomy community. So what Karthik explained earlier with the embedding is known here, it's part of a data ingestion pipeline. So imagine you have these PDFs, you transform them into text, then you cut them because you want them in smaller chunks to be fed to an embedding model to move them into a context-aware representation. So think about these very meaningful vectors that live in high-dimensional spaces. And then you put all these vectors into a vector database. Now you go to the chatbot or to your pipeline and you ask a question. This question also gets transformed into a vector representation. And then you compute the similarity between the embedding representation of this question and the vectors living in your vector database. This is a cosine similarity. Now that you have a sense of how close or far away things are from each other in this high-end space, you can say, okay, I want you to give me the top 8 closest. So you retrieve these papers. Once you have retrieved these papers, you feed them to GPT-4 model, as we have done in this particular study, and then we get an answer back for our question. But here's where the catch is. So here's why we think this technique is very important. Because, for example, if you ask a question like this, where do you expect to find all the stars in the Milky Way? Then it might take a while to read annular review. It might take a while to go through all the literature to find the answer for these questions. With this approach, we have an instantaneous approach to the same problem. We can ask the same question, and then we can use this virtual PI bot or a variation of this bot to answer us this question. And this tool is actually something that we employ in our AstroML group at ANU. And it's actually proven to be exceptionally useful for our research. It gives us meaningful references, as Karthik showed, and he also provides a quite nice overview of what's been happening in the literature. But what I've been telling you so far deals with the past. People have been writing these papers, and what we try to do here is to retrieve information in this paper, modulated by a large language model that is very context sensitive. So in this way, you can think about this as intelligent information retrieval. But I think right now we are in a position to try to look forward to the future, not just to retrieve information, but actually create new information, or create pathways for us to come up with new ideas. So in the pipeline that I showed you earlier, where you have the data, you move it into a vector space, you compute the similarity, you get the context, and you get an answer for your question or for your query, I thought about what if we change the focus? What if we say, hey, I want you to give you an idea. I want you to give me an idea drawing from gaps in the knowledge that you've been provided with on a particular topic. And then my model comes up with a good idea, right? But then I noticed that if you take another model, an adversarial GPT-4 model in this case, and you give it access to the same body of knowledge, and you say your job is to criticize the idea that you have been fed, will the answer improve? So that is a question that our team proposed 2 weeks ago. And our results are, of course, this is work in progress. We need to evaluate this further, but our results are promising. So here on the x-axis, I show you the number of papers that you use. On the y-axis, I show you an evaluation score. That corresponds pretty much with 1. If it's a very bad idea, GPT-4 is done with. No more. 3, it's a first-year grad student. 5 is an expert. And we employed human evaluators to assess our hypothesis. What you see here is NF is 0 means that this is the original answer of your model. NF is 1 is the answer that it gives you, the idea that it provides after one feedback loop. So it received the criticism, and it updated its state based on that criticism. And from this very very small study, what we can see that for 1,000 papers, you can see the mean has moved upwards, and also the standard deviation has shrunk. So in a sense, the model gives you much better hypothesis without as much variation on that score. In a similar way, we didn't only want to look at the hypothesis, and on my personal experience being in the matrix for 3 days with GPT-4 doing this project, I noticed that the hypotheses were good and we're happy with them, but what we were really impressed with were the critiques the model had to those hypotheses. So you can imagine already, I want you to imagine a scenario where you have an idea and you go to this very smart co-pilot that you have, the research co-pilot, say, I have this idea, can you tell me what the weaknesses are? And again, this tends to scale with the number of papers that he sees. So for 1,000 papers, we are already looking between quite expert level critique. Again, this is of course sensitive to the evaluation method, and that's why we're here, because as a community we want to talk to you about how can we create better and more robust evaluation techniques. But I think it's already quite impressive that we can even still be thinking about this. All right, but before I want to show you something else. So here, what I did, I took all the 1,000 papers, right? And I took their abstracts and I embedded them. I projected them in 2 dimensions here. And in the black box here, you have the answer, where the answer lives in the embedding space. So I took the answer, I also got the embedding for the answer, and then I show you here the 8 closest abstracts to that answer. Once we move to 100 papers, we get this, you see that this polygon has grown. And of course, I know we are working into this, so this is not necessarily like a direct representation of the size of the area in ND, but for visualization purposes, it's quite an important observation. When we go to 1,000, polygon has grown a lot more. But an even cooler representation is what happens here. Here we have an answer shown in the black polygon, and in the line, I show you the critique to that answer. So similar, I take the critique, I embed it, and I compute the 8 closest neighbors to it, and then I draw that line polygon next to it. What happens is that the model has updated its answer, so now the black line grows in the direction of the critique. And then I ask the model again, hey, can you critique the new answer? And then it starts drawing from different parts of the space. And the final answer seems to be growing even more to follow the critique space. So this is one way you can use embeddings to try to understand what your models are seeing and what they're doing. So at the very end, this is the question we want to pose on behalf of UniverseTBD to you. What do we want as a community? Where do we draw the line? Where do we push the line? And fundamentally, what can we try to create such that it helps us all to try? But of course, this raises a lot of questions on ethics, and we have Josh here who has shown us yesterday that we need to stop and think about the implications of this type of research. And that's why I think we're very excited to have you here. And please, for that reason, I want you to check the Slack CFA to answer the latest ideas question and give us ideas on how we can take this further. Thank you very much.
Thank you, Joe. Oh, okay, we got questions. So let's start from Rosette.
Thanks. I mean, this is very intriguing. One of the concerns that I have, it comes out of something that we're actually trying to do with machine learning, which is that when you do the embedding and you find the clusters, you know that you have certain things in common that you're happy about, but we don't know that some of the most interesting things actually didn't appear in that cluster, right? They could be someplace else. And so in this much more sophisticated work that you're doing, where you're looking at ideas, you're putting together all of these papers, we all know from the history of science that many times the most forward-looking thing, the thing that people are going to be looking at 50 years from now, is a paper that does something different from others and isn't cited very much, and probably, my guess would be kind of isolated someplace out there. And yet, if we had a technique that could find those types of things, that's where, maybe the work that you're doing would lead to big progress, as opposed to the kind of incremental progress where you're just answering the next question that everybody has, right? So I just wanted to get some feedback from you on outliers in the applications that you're doing, things that don't necessarily appear in clusters.
Thank you so much for your question. I think that's a great insight. To be honest, we have started thinking about a variation on that. So, these great ideas that appear in science, how can we actually get them, how can the model get them before they happen? So what happens is that if you think the papers are indexed by time, so what we were thinking, take maybe 10 years ago, train the model, let the model see those papers and see if it can actually predict the next 5 to 10 years. And maybe I don't have an immediate answer to your insight into your question, but I think we can actually use that approach to try to identify the outliers that maybe drive if you add an outlier into that model scope, how does the hypothesis that it generates aligns more with what has actually been proven to be extraordinary?
Sometimes it takes longer, though. Look at Bell's theorem,
Absolutely.
for example, right?
Yes.
So you have a paper that's extremely important, but it's not really getting much attention until 30, 40 years later.
Yeah.
If we could really have, had people place more emphasis on that earlier,
Yep.
it would have changed the course of some areas of physics, and many people would have had more productive careers.
Absolutely, and that is an extraordinary idea. Our hope is to create some sort of infrastructure that people can use, and you can drag and drop outliers, and then you can get the hypothesis, and then we hopefully get your feedback, so then we can sort of tune things for better. Hopefully, I think that's our hope, and that's why we're here. Thank you.
Thanks to the three of you for a really nice demonstration. So in all the examples you showed, it looks like you were able to actually take the text, generate the embeddings, and then in the case where you actually ask questions, I guess you had to somehow pass it through the decoder so that it could generate new content or something like that. But we don't have access to the GPT code. I am wondering, from a carpentry point of view, how do you actually interact with a model when you don't really have access to what's really happening behind the scenes?
All right. Yes, that's a fair question. I think we interact with the GPT-4 model through an API. So we don't have access to the architecture weights, but we can still use it for prediction, for generation, for next token generation. And there are, of course, open source models that you can use, such as Llama. I hope that answers your question. And hopefully we are building a website, and we're going to show some tutorials on actually
A tutorial would be great. Yeah,
yes,
thanks.
Brilliant.
Yes, that was a great talk. Thank you. Yes, I was wondering if I understood correctly, you're doing a lot of work before you prompt ChatGPT.
Yes.
And that's what helps you get a more reliable question.
Yes.
Right? I have two questions. So one is, does it never give you a paper that does not exist, somewhere in between two papers? And would it be worth making a model, a posterior a model after your output from ChatGPT, similar to the constitution that they have, that is to comply with the rules and ethics and stuff, but instead of that, making a posterior model to make sure it's reliable and focus there to make it rigorous and consistent with the literature.
We can only hope to achieve that, of course. I think one approach to answer your second question, to start with your second question, is what we call domain adaptation. So in some way, we want to take an existing model like the GPT-2, which is actually available, and we have someone in the UniverseTBD working on it already to give it the astronomy, some subset of the astronomy corpus, and let it learn directly from that. So it adapts itself to the astronomy literature. And in that, we hope to minimize the amount of hallucination and of missed issues there. Yeah. And for your first question, I think Kartik might be more, because you've interacted quite a bit with the hallucination aspect.
Yeah, so the way we have currently constructed it, there's always this trade-off between how expressive you want the model to be versus how true or like the veracity that you want from the model. And we essentially stuck to the side of only summarize the result, like everything else, like finding papers, actually happens in the embedding space. So it essentially like doesn't have any opportunity in that framework to hallucinate, because we don't give it the chance. We only like GPT only takes the final sort of curated information pool and condenses it into a coherent answer to the question that we ask. And I can also do the demo if
Yeah, absolutely.
Should we? Okay.
Yeah, while I answer questions.
Yeah.
Yes. Any more questions? Oh wow.
You can take a plug in.
Yes. Vivek? Or-
So kind of in the same ballpark, is there any work, probably not by you, but in the broader community, about sort of, can we render the answers that we get out in forms other than sort of literate human prose? Because I always worry that, these things end up being rendered in words that sound very authoritative. You call it the virtual PI, so it's very easy for a person to be like, oh, it sounds authentic, so I must trust it. Whereas, like, honestly, I think it might be better if it was sort of written like, peak, say, redshifts, good, in a way that, like, kind of encourages people to realize that this is not an actual human saying these things. So are there ways to sort of get outputs that are in a different form than lengthy paragraphs of annotated text?
That is a great question. I think Janssen might want to take that one, because virtual PI, to be honest, we called it virtual PI because the PI was away at the time, the human one. And we kind of missed our PI, so... But of course, we want to incorporate uncertainty into the model answer and use that as a way to guide the answer to the human.
Just to say, we were just talking about this yesterday morning, which feels like 1,000 years ago at this point. But one thought was that it would not be that hard to say, please answer this in the style of, and choose, the person that you're used to interacting with. Because, one thing we discussed is, for instance, for SciX, there might be a lay user, but there might be an expert within the discipline, but there also might be somebody who's out of discipline. So the way I would like an earth science question answered is not as if I am a high schooler, but as if I am an astrophysicist who, knows some stuff, and I'd love you to translate it into my language. And that, we're not far from that. That's a very interesting angle.
There is no problem.
I'm curious, like, if you give them like two questions with similar context but different different words, will it like show the same results like paper? Like if you ask like the star forming main sequence and like specific stuff, like give like two different words but like same science, will it like understand what we're asking for?
We only hope to do so if our approach is robust, because we hope that the two questions live quite close in the embedding space. So therefore, they should retrieve similar papers. But this is something that we have not evaluated, and I think it's a great idea. And we probably should try this to see how much the answers diverge depending on the similarity of the input.
Yeah, I guess one of the key things about an approach like this is that we can test exactly that and hopefully find things. So like anecdotally, yes, but that's not an answer.
Can you do it now?
Sorry? Yeah, like we can also try things now. So this is essentially the rough sort of streamlit version of what we have been playing around with, and there's two parts of this. There's the archive embedding itself, where you can just go and just hover over papers and see what's sort of in the different parts of the space. And you can essentially, if you know what you want, so if you want to look for quenching, for example, then you can actually search for that and see where those papers are specifically. So it's like, okay, that's sort of the rough location where papers of that subject are. And then there's the paper search, where you can ask it a question and tell it like, show author information, show me summaries, and let it run and give you outputs. So these two already are there. The website's iffy, so if too many people access it, it still crashes. So that's something that we need to fix at some point. But the third part that I haven't gotten up and running yet is, or like, I have it running locally, I don't have it running on the internet, but hopefully in the next few days, is to do the sort of question answering. So if anyone here has questions that you want to try asking, and see if it makes sensible answers, or see if you can prompt it to hallucinate, right? That would be, we can do that.
Where's the microphone? Great demo. Are there any more questions? To any? Okay, we have one here.
It takes a bit.
Hi. So I'm interested in the adversarial GPT,
Right.
and I'm wondering, because the field goes through a referee process, right?
Yes.
This is very natural.
We all like referee number 2. Yes.
So, sorry?
Yeah.
Okay. Yeah. So, I mean, can you, for example, look at like archive version 1 versus archive version 4, whatever, and kind of see what happens there, or ask journals somehow to get involved in this training so that you have access to the referee reports, anonymized or something, whatever. But then have kind of a feedback loop that's already like improves the training data set.
Absolutely, yes. So I think that was our hope as well. We didn't go quite as far to envisioning how this is possible. We definitely want to have a human critic in the loop. So we have the model critic, and we want to also have the human. And that feedback from the human, we can sort of try to use to fine-tune. So we have a model that's actually fine-tuned to generate ideas on the best available data there is. So yes, we are thinking about it. We just are not quite sure on how to ask for these data sets yet.
Right, but I mean, could this even be like a whole other layer? Because each paper has a referee report.
Yes, yes.
I think one idea that we have been floating around is, of course, it's very hard to trust. Yeah, it's very hard to trust the hypothesis, but it would be nice if you can have a referee, right? So if you have a bias like NSF, like reviewer, you would say that alignment with the consensus seems to be a bit off. Like you might want to like double check. You referee the referee, right? So I think that's one idea that we have been like floating, and there's another layer. Again, the sky is the limit is what you want, and how we fine tune that. So there's a prompting. We are looking at fine tuning. Really, the sky is the limit is what the people want. Yeah.
I just have to preface what I'm going to say by I am a huge fan of this, and I think this is the future. Okay, this is a terrible answer. Okay.
This is exactly the feedback we need.
Right. No, but I think part of it, and this is a real question for Alberto, because what this is a question about is more like what is the initial mass function? So it doesn't really say anything about what determines. It says and the shape of the stellar initial mass function. It's not an answer to what determines the initial mass function of stars, right? But you told me yesterday, I think this is only searching abstracts, or is it right? And so, Alberto, my question to you is, this is a hard question. So I think everybody here wants to know, like, if I go to ADS and press, magic search, okay, and I want to ask questions like this, when does that happen and what does it do, right? And how well can I control it and go, no, that part's wrong, give me something else, et cetera. Like this is right. And that relies, I think, on the full text of 120 years of articles. And so the question is the legal, political, publisher-y question. So what are we going to do, Alberto?
So yeah, that's exactly, the crux of the problem, which is ADS has collected the full text for essentially all the refereed literature in astronomy and other areas. There are agreements that we have with publishers in terms of what we're allowed to do with the full text. One of the main function of having the full text is for us to be able to enable search and discovery over this content. So to the extent that we can use large language models to accomplish that task, we're fine. To the extent that that content, which is in many cases copyrighted, can be used to generate things that people then take and copy paste in a proposal, that presents a problem. And so we are, in fact, reviewing many of the agreements that we have with the publishers to exactly define what we're allowed to do with copyrighted content. Now, most of those restrictions go away when you use content that is licensed with more liberal licenses like CC BY, where you can just reuse that content without restrictions. So there is a scenario in which we'll be able to do a lot of this using maybe not 100% of the literature, but enough of it that you get things such as reviews and advice and critiques without necessarily knowing, violating something or having legal problems associated with this. The one thing that I would say from my perspective that we want to guarantee is that what you get out of this system is truthful. So hallucination is just not something that we can tolerate. And these are the early days, so there's a lot of progress that can be made. We're not going to replace your job with a ChatGPT, but hopefully this will make everybody more provide insight and critique, especially to someone who's entering a new field.
Can I just ask one more question?
Yeah.
I have to ask for the microphone. Just to follow up something I didn't say, but which is related to that, is what I personally want is that everything that this tells me is then cited and linked back to where did you get this information,
Correct.
which is my huge objection to ChatGPT 4 the way it is now, and we discussed this yesterday. And so I think you are all hoping that every sort of claim that's made can be linked back to an actual article. And so in that case, Alberto, does that change anything with the publishers if their articles are cited?
The short answer is yes. So in fact, with someone who's working with us here, Harry Bloom, who is going to manage is our publisher liaison, so he's the person who's reviewing many of our agreements. And that seems to be one of the critical components of this, is that if the information from a particular paper was used to generate an answer, then that information needs to be transmitted to the user in the form of a citation, because that's what's of interest, both for scientific, but also for credit purposes to that particular publisher. Yes.
Somehow, Alyssa's question sparked something else in my mind about the way the presentation is given. And that is, as you know, as scientists, we often learn the most from a paper from its graphs, right? It's the figures, or sometimes now the accompanying videos, that actually teach us the most in the least time.
Right.
And you could even imagine a system where you take figures from 5 different papers and take the data points and put them all together, have a system like this put them together. So my question is, are you thinking about graphics, or is that something that's not yet approachable?
I think step by step, yes, but yes, definitely. I think right now multimodal large models are there. They're happening. GPT-4 will soon have a multimodal possibility, yes, but there are also open source models that achieve the same. So once we fix text very, very well, so we can't afford hallucination, we can't do all that, then we can move towards figures. And the cool thing with figures is that we have the perfect image to text translation there, because we have the captions. So in that sense, we can use text to anchor our understanding.
And there is a project to do that. Jill Nyman is there with Peter. Very quick.
Thank you.
One last question. No, for me.
Okay, super quick question. Are the citations, or the number of citations, or the papers that cite a paper going into the embedding as well? Because I'm worried that could perpetuate biases. And the more you get the paper out, the more it's going to be cited, and then you're going to perpetuate the first trend of a paper.
Yeah, I think we were talking about this at some point. Yeah,
Top question, but of course the goal of this is to yeah. So like, the goal of that is exactly to counter that. It's never perfect, but if you search by context instead of search by citation, I still like looking for things like okay, Google search. I look like rank by citation. That is a very bad way to perpetuate that. So this might not fully like counteract that, but it's very easy to say, you know, I want to have some ranking that gives some weight on paper that is highly relevant but undercited to democratize. Yeah, so one of the things that we didn't talk about is really like democratizing the field, because not many people are in CFA, right? Where you have Astro Coffee, that many people are stuck in their big school teaching, and this is the co-pilot that desperately like need to do the best research they can. And this is one of the main goals why we do this.
Absolutely, thank you.
Thank you. I think, and with that, we'll conclude the talk. Thanks again to all of our presenters. Just a note that Joe will be here for next week. And you are
You're only today.
today. So you have 1 hour to talk to these two guys. Thanks again for participating.
Yeah, absolutely. Yeah. It's great. Thank you so much. I hope it was okay that we had a multi-agent talk, because I thought I wanted the